Can you see the presentation, please?
Yes, you can continue. Yes.
Okay, thank you very much. So first of all, thank you for letting me present just before Mr. Liu. Thank you very much because you know the time difference is 10 hours. It's now it's more than midnight. Thank you very much. So my communication name is named Modulations classification based on neural networks algorithm in communication intelligence. So it's a great pleasure to present this work before you. As outlined, I will begin with an introduction to let you know about this paper. I will then talk about literature review, then methodology. After that, we will evaluate and show you the experimental results. And after discussions and perspectives, we will end by conclusion. So the teamwork is comprised by 5%, there are 5 engineers, PhD, and the professors in the university from Morocco. Let's please now set the stage by understanding the landscape we navigate. I would like to explain you how is it exactly. So communication signals are marked by the use of diverse modulations to achieve high data rates while mitigating interference. They present a formidable challenge for intelligence systems tasked with monitoring the communication spectrum. So as a definition, the communication intelligence, which is comment, is all information gathered from the communication interception by a receiver. As modulation become more complicated with the new telecommunications technologies, as satellites, smartphone, etc., the processes of identification and demodulations become progressively very complex, which is a huge challenge in the domain of signal intelligence, who is really relying on accurately determining the modulation used for transmitting radio signals. So why we need modulation? For 4 points. The first one is transmission efficiency. It allows the transfer of information over a channel or medium by modulating a carrier wave, which is a sinusoidal wave, with the information signal, which can be analog or digital. Digital, it means a byte stream, and it becomes very feasible to transmit the signal. The second point is the bandwidth utilization. The modulation helps in utilizing the available bandwidth more effectively. Different modulation techniques permit multiple signals to be transmitted simultaneously. The third point is signal integrity. It maintains the integrity of the transmitted signal. The modulation techniques make the signal less susceptible to noise and interference. And the last point is the compatibility. Different devices and communication systems might work on different frequency bands or use different modulation schemes. Modulation facilitates compatibility by allowing the translation of signal between various systems. In essence, modulation serves as the bridge between information signals and the transmission medium, enabling effective communication across various systems and environments. We can either modulate a signal by putting the message either in modulation, frequency, or phase. As you know, the formula of a signal is amplitude times sinus WT plus phase. So we can modulate using amplitude, frequency, or phase. So for example, I will give you some example. Just if you want to send just 5 bytes. Imagine 0, 1, 1, 0, 1. So the signal to transmit is this one. See the value of 0 and the value of 1. And normally we cannot send this like this. So we need a carrier which is in a very high frequency. And we can do it by 3 ways. In amplitude, for example, here, we have 2 values of amplitude. The smaller one, which is 0, the bigger one, 1, 1, and then the smaller one. The same thing applies with frequency. So this one is higher frequency, is a lower frequency, lower frequency, and this is higher frequency because you see the spaces between the waves are smaller. So the same thing, 0, 1, 1, 0, 1. So if the variation is continuous, we talk about analog modulation, and if it's discrete, as we have seen by byte stream, it's digital. Now I'm going to show you just a normal case of transmission. So for example, for analog communication, if we want to send, for example, voice, it goes into a microphone, gets amplified, and then modulated either in frequency or amplitude, and then amplified and sent via an antenna. So in the process of reception, so the same thing, it goes into an antenna, gets amplified, and then the demodulation, which is the inverse of the opposite of modulation. So now we are trying to get the information which was mixed to the carrier. For digital communication, it's more complicated than normal analog modulation. So here we talk about an input signal, which is digital. So, and then we have source coding, channel coding, and then modulation. And in the reception process, so we receive the signal here and we demodulate. And so the source coding is much about removing the redundant data. It's a way to simplify the information that we are trying to send. The channel coding is more about adding some extra bytes to preserve the integrity of the signal. And modulation, as we have seen before, it's translating the baseline signaling to the high frequency by mixing it with a radio frequency carrier. And demodulation is the opposite. It's removing and extract to the information from the signal. So in our work, we have worked with some specific data. So we have opted to use raw data that we can extract from a receiver who receives the information from the electromagnetic waves. What is IQ exactly? IQ, it means in phase and quadrature. As you know, a normal signal, it's equal to amplitude times cosinus WT plus phase. So any signal we can split it into two components. The first one is the in phase. As you can see here, it's normally the cosinus. It's the as you can see here, the I, it's the blue, and for the quadrature is the sinus. So a normal signal, it comprises two components, the in phase and the quadrature, and it's very important above all in modulation, because we need to for the modulation of phase, we need these two signals, because we are going to modify the phases of the signal in order to transmit the signal. We are looking for some states in the phase, the amplitude, and also the frequency. and we are trying to send the message. So let's now talk about the literature review or the state of art. So excuse me. So in the early days, modulation classification resembled solving intricate puzzles. So the likelihood-based methods were our first attempt, where we tried the machine-received signal with predefined likelihood functions. Think of it as crafting as a unique key of each modulation types, an approach laden with complexity and computational demand. As our journey progressed, we embraced future-based techniques. This involves a two-step dense reprocessing signal and extracting relevant features. However, challenges arose with manually crafted features and the limited learning capacity of conventional algorithms. So as you can see here, the input signal, we can extract the features. Sorry. And then we can get which modulation it is. It is by amplitude and phase, or this one is in a amplitude or phase. Sorry. So there are many approaches using deep learning, which is exceptional data processing capabilities. So the revolutionary breakthrough came with the advent of deep learning, featuring the formidable arsenal of deep learning networks. So there are many papers and works talking about the problem of the classification of modulations, and many doctors, many researchers have made so a big advances in this problem. So they have used the CNN, recurrent neural network. So this technology promises boundless potential. Ushering is a new era in signal processing. However, amidst the optimism, inherent challenge, particularly on the form of the overfitting, cast, and shadow, or the seamless integration of these powerful tools. So for the background and our advanced approach in deep learning. So in the other previous works, there was always a challenge in some kind of signals. The signals where there was a low signal to noise ratio. As you can see here, this signal is very noisy. So it was noisy in the transmission, on the reception, maybe some atmospherical conditions. So here, these are the channels, and the accuracy of classification was very low in this kind of classification. So so as we are seeing here many deep learning based AMC automatic modulation classification methods have predominantly focused in high signal to noise ratio signals. So they have reached really some good results, but they have neglected the channels posed by noisy signal, because the medium of transmission, we will always find this gap. So this problem of noise. So the goal is for us as a team is to develop a robust end-to-end deep learning model capable to classify the signals in the whole spectrum. So regardless of the signal noise to ratio. So our methodology, the proposed approach. So after many months, we have tried many approaches regarding the problem of this noisy signals. So we have now a revolutionary solution, which is an ensemble learning. This ensemble learning is a powerful paradigm in machine learning. It holds immense significance in modulation classification by addressing the complexities that we have talked about previously. So it involves combining prediction from various methods to improve overall performance, guaranteeing increased robustness and accuracy. So this proves indispensable in scenarios marked by diverse characteristics, including the problem of signal-to-noise conditions. Oh. So our proposed approach for the moment is a fusion between a residual network known as ResNet, and also the second one is the transformer neural network, harnesses the strengths of both architecture of a comprehensive modulation classification solutions. So for the ResNet excels in capturing spatial features, making it proficient in discerning intricate patterns of high signal to noise ratio conditions. On the other hand, so the TNN is specialized in handling sequential data and temporal dependencies, making it highly effective in low signal to noise ratio. It means that when low signal to noise ratio is a very noisy signal. So the architecture of our ensemble model is designed to leverage the complementary strengths of ResNet and TNN. So ResNet, optimized for high SNR, contributes by extracting, as we have said, spatial features, while TNN tailored for a very low signal to noise ratio. So the reason behind this combination is the ability of the two algorithms to compensate for each other's limitations. Donc, the ensemble model takes advantage of both model capability, providing a robust and adaptive classification approach. The unique aspect of our ensemble model is the simultaneous prediction of both ResNet and TNN with a decision-making mechanism that selects the maximum prediction as the final output. So this dynamic approach ensures that the ensemble benefits from the strengths of both models, providing so a good solution for our problem. So now let's go deeper in our proposed approach. So the residual network, the ResNet, is a convolutional neural network, CNN architecture that overcomes the vanishing gradient problem, which is a problem that many CNN algorithms are facing, making it possible to construct network with up of thousands of convolutional layers, which outperform shallower network. So the main difference is the shortcut connections. The shortcut connections that they can helping. So as you can see, it has a trick called shortcut prediction. It's like having little shortcuts between layers. So if one layer makes a mistake, the shortcuts help it to fix it. This makes learning easier, especially when the network is really deep, and we can avoid the problem of vanishing gradient. And and for the processing, it was really quicker than a normal CNN, and with good results, as we are going to see in our experiments results. So for the transformer neural network architecture, so it's comprised several layers, including the encoding and decoding. So the encoder is composed by multiple layers. As you know, the TNN, the transformer neural network, is actually very known. So it's there is a very famous book about this. It's all you need is attention. So the principle of the TNN is the attention. It means that there is some layers. They are looking for some important parts of the signal for our case. So the encoder is composed of multiple layers of self-attention and the feed-forward neural network. The self-attention mechanism enables the model to weight the importance of different input components when making prediction. So as we have said before, this was our solution for the very noisy signals that the ResNet cannot really make a good prediction. So the feed-forward neural network is used to process the output of the self-attention layer. The decoder also is composed of several networks of self-attentions and feed-forward neural network. The decoder also uses a mechanism called masked self-attentions and feed-forward neural network. The decoder used the mask self-attention for the reason that is preventing the model from picking at future tokens in the input sequence when making predictions. The transformer architecture also contains multi-head attention mechanism, which allow the model to attend to various parts of the input at the same times, improving its ability to understand the input. It is, we can say that it's highly parallelized and computationally efficient. So each model independently processes the signal and generates a prediction. The ensemble decision-making mechanism is then employed, where the maximum prediction among the two is selected as the final output. And the ensemble learns to dynamically adapt to varying challenges posed by different cases of signal-to-noise ratio condition, making it versatile solutions. So indeed, architecturally, the ensemble model is enhanced to accommodate the dual prediction and give a good decision making process. So let's now talk about our experimental results. So the data sets consists of the following key components. So we have used synthetic data. So the synthetic data, which comprise 24 different modulation types. It was about frequency, amplitude, phase, and combined modulations. So reflecting complexity of real-world communication, even if it was synthetic, and it was in different scenarios of signal to noise ratio and low fading channels environment were also included. So for the state of arts, normally the researchers make experiments on this kind of synthetic data, but for our case, so we have complemented by real-world gathered data. So we have used some real signals intercepted from various kinds of radio transmissions, satellites, communication systems. So we have added 44,867 frames fade in channel environments. So we have almost a total of we have more than 2.6 million samples. So the data set was really a huge data set with many scenarios of signal to noise ratio and many modulation types. So that was a challenge for us. above all for the real data, you should intercept the information, the signal, and then you have to labelize it and tag it. So for our tests, so we have partitioned into as usual in training about 80% and testing 20% sets, maintaining a balanced distribution for unbiased model evaluation. It provides 26 levels of 26 SNR, signal to noise ratio, for each modulation tips, comprising 4096 frames for each modulations combination, with each frame containing 1024 complex time series sample, ensuring a thorough exploration of noise condition across various modulation types. So in our experiments, we meticulously addressed the individual performance of ResNet. So ResNet was very excellent. So as you can see, the accuracy. So accuracy 6, it means signal to noise ratio 6. This one. So for 30, it means that the signal was without any kind of or a very small amount of noise. But from this noise of this signal to noise ratio, so the accuracy was lower, as you can see, 77%. But for all this category, it was a very good accuracy for the, as you can see here in the confusion matrix. So here you can see the types of modulations, and it varies. So now they are the noisy signals. Now we are coming to the strong signals with a very high. So we can see it. The results are very good. Now for the TNN. So that was the most important part of our work. So similarly, though, we exhibited that TNN gives a very notable proficiency in low signal scenarios, and normally in the state of arts, this kind of signal, there was really not really good accuracy, or some doctors or some researchers, they don't really try to find the solution for this kind of noisy signals. So as I said, it exhibited a remarkable ability not only to reconstruct input signals, but also to accurately recognize them. So the TNN was really a very good solution for this kind of noisy systems. So now let's talk about the combination, the ensemble model. So as you can see here, for the very noisy signals, from -20 to -2. So we have accuracy around 70% to 72%. And then when the signals becomes he has more strength, so we have 95%. So the true game changer when we introduced our ensemble model, seamlessly combining ResNet and TNN. So it gives a very good performance. So as a discussion, so in the realm of practical application, our research unfolds with significant implication for modulation classification in the domain of communication intelligence. The robustness of ResNet shines in high signal-to-noise ratio environments, accurately discerning intricate and complex spatial features within clear noise-free conditions. On the flip side, the transformer neural network showcases its effectiveness in low signal-to-noise scenarios, deftly handling sequential data with precision even amidst a high noise level. So, as we said, the ensemble of ResNet it has leveraged the respective strength results in a robust solution with improved stability and accuracy, a high adaptability across the spectrum, even in some noisy parameters. As conclusion, we can say that automatic modulation classification, EMC, plays a pivotal role in communication signal processing. Above all in the domain of of communication intelligence, where normally we don't know what is the modulation used. So we are gaining significance in fields like cognitive electronic warfare and cognitive radio amid the rise of artificial intelligence encompassing deep learning neural network. So this paper introduces an end-to-end deep learning model for modulation signal classification. The model incorporates an ensemble learning network to enhance stability and integrate predictive features effectively. Our approach involves leveraging the strength of 2D deep learning architecture. So as we have seen, the ResNet and the TNN, the transformer neural network. And through a comprehensive experiments, our proposed deep ensemble method showcases superior classification, recognition, accuracy, and stability across the spectrum and signal to noise ratio, encompassing both high and low SNR scenarios. So for our perspective, so once we have achieved a good recognition of modulation, we are now working. So before we're gonna say that now we are able to demodulate the signal. So once we know the modulation, we can analyze the signal and extract from it a bit stream if it's digital. So now we are going to have a byte stream. Our perspective is to apply the similar methodology. So methodology, I mean here, the AI, artificial intelligence, using neural network for the classification and recognition of coding and encryption of the signal. So after you get the signal, normally in many cases, the signal will be coded. So now you need to know which code is it. Is it Bodo? Is it something different? So, and also if it's encrypted, so now you should know what kind of encryption it is. So the classification of encryption, if it is AES 256, which is yet RC4 or other kind of encryption. So now our future works will focus about this. So this approach will save more time and facilitate the decoding and decryption of any signals in the domain of communication intelligence. So thank you very much for your attention.